All right, so as I was saying, to the people, maybe those of the people on YouTube who just tuned in, I'm a postdoc at Drexel University in Philadelphia, and we do processing of images. You'll see some of the movies of things we do in my lab. And we mostly use MATLAB, but I was curious, I've been wanting to learn NumPy and SciPy for a while, and it seemed the best way to learn it because I wasn't having time to do it at work really was to volunteer to give a talk on it. So that was kind of the motivation for this. So the point of what I'm going to try to give you is a kind of a feel for what you can do with NumPy, and you can't really do very well in Perl. So the disclaimer is that there's not really a whole lot of Perl in this talk. There's a lot of Python, and I do make fun of Python in a few places. But I have to say that I do kind of, I'm not a huge fan of Python. I do like NumPy and what they can do a lot. I don't know if you can read that in the back. The slides will be online, or you could just do what I did and look through Google or look through XKCD for Python, and you'll find that. We do in my lab at Drexel's what we call computational image analysis. And so that means that sometimes I read papers that say this, and I'll just read this if you can't say it. It says, the NL means algorithm, which is defined by the simple formula, and it doesn't really matter if you can even see this. I think the point is that it's not really a simple formula. It's a ridiculous integral, and I have no idea what it's supposed to be doing. Mostly we get movies like this from biologists that we collaborate with. And those white things are hematopoietic stem cells. They're part of the immune system, and it's normally really hard to get them to grow in a dish like this. But the way they got them to grow is they're growing in this culture of something called OP9, or oligodendrocyte precursor cells. That's what those things are in the background. So they get them to stay alive for a few days in a dish, and they take time-lapse pictures of them. This is about 4 or 5 days worth of growth for them, which is kind of cool. So like, how do they even do this, right? I mean, when I was in high school, we'd had microscopes that didn't even look as fancy as that, but the pictures that you get out of a normal microscope, they're really hard to use, and they're just like visual things. You're just looking through them and seeing things like that. But modern microscopes are a lot more sophisticated. Things can grow inside there. They can take pictures of them automatically. And that movie that we got was really, they don't really send us a movie. They send us thousands of frames that we can kind of put together to make a movie out of them. And there's a couple of cool things with them. One is something called phase contrast microscopy. And some cool stuff with physics. I encourage you to read the Wikipedia page on it. Basically what they do is they shine some of the light through the lens and some of the light around the lens, so it's out of phase, and you get much better contrast. Someone named Fritz Zernike won the Nobel Prize in Physics for this in 1953. And basically, you can turn an image that looks like this into an image that looks like this. And if we want to find all the cells in one of those movie frames, it's much easier to work with something like this than something like that because the edges are a lot sharper. The other thing that we use a lot is based on this. Does anyone know what this is? Jellyfish. It's a particular type of jellyfish. It's a crystal jellyfish, or Aquiora victoria, and it's a bioluminescent jellyfish. So when ultraviolet light shines on them, they glow in different colors. And biologists were able to isolate the protein that does this, and they call it by the great name green fluorescent protein. But despite the name, it actually can get lots of different colors from them. So you can try different wavelengths of light and get different colors out of them. And you can use them to make cool tricks like have mice that glow in the dark. Or you can take these proteins and embed them actually in cells and have them only turn on when certain other proteins are activated. And they're really useful for all sorts of things. They do have this, one of the problems with them, like unlike the mice, these mice here, when you put them into cells, you have to shine ultraviolet light in those fancy microscopes in order to get them to glow. But if you shine too much ultraviolet light on cells, it tends to kill them after a while, which is why our experiments only run for a couple of days. And often we don't even have fluorescence on every one of the frames. Maybe every 30 frames we have fluorescence. So we can take a movie. I realize this is kind of hard to see. The contrast isn't so great. But this is a movie much like that first movie I showed you. And we're able to take that information and build a lineage tree out of it. So we followed, at the beginning, there was just one cell there. And by the end, there's going to be lots and lots of cells. And we can kind of track them as they move around and divide, and build a lineage tree out of all of them. So like a family tree of all the cells as they're dividing. So, biology is kind of cool. There's interesting problems that we can use as programmers to work with biologists, not just the bio-Perl type kind of textual stuff, but image analysis type stuff as well. This is another cool XKCD thing about biology. And this is my ad. We're hiring too, but we're hiring grad students and postdocs, so you won't be making as much as you will working for our friends at some of our wonderful sponsors outside, but it's kind of cool and interesting work. So this is mostly where I spend my day. This is MATLAB, although I'm not using it on a Mac. I'm using it on a big Windows box, so it's not all scrunched up quite like that. So if who's used MATLAB before? Lots of people have used MATLAB before. I have this love-hate relationship with MATLAB. I used to just totally hate it. I mean, I used to just totally hate it. But I've come to, I guess, to respect that it's really easy to do some stuff in it. But I don't know. It's like Visual Basic, I guess, where like it's really good to like sort of play around with it and do stuff. But we have a big application, and it kind of breaks down after a while. It just doesn't. It doesn't expand to supporting big projects very well for all sorts of reasons, which is what got me interested in NumPy. A lot of people I know at Drexel and elsewhere in academia have started in MATLAB, and when the project kind of outgrew MATLAB, they moved to NumPy and SciPy. And I'd heard so much about it, I really wanted to learn what all it was about. So what are NumPy and SciPy? So NumPy is what I'm mostly going to be talking about, is a Python module that lets you do fast vectorized operations on arrays. And I'll talk about what vectorized means. And then what SciPy is a whole bunch of mathematical and scientific modules that have been built on top of NumPy to do lots and lots of things. And I'll talk about some of the applications at the end of the talk. As I said, I'm going to talk a lot more about NumPy than SciPy. But just to motivate this, let's say that we want to compute the pairwise sums of two lists, A and B, of equal length. So A and B are lists of numbers. They have the same length. And we want to make a new array C of the same length where we're just pairwise adding up all the elements in them. So if we had C code, we could do it something like this, where we just loop over we know how many rows there are. We have a simple for loop, and then C sub I equals A sub I plus B sub I. Perl, we could do it. We don't have to know how big it is because it's already there in the $pound $A, and we can just push things in there. So that's fine. Python, the idiom's a little bit different, but we can do the same thing. But if A and B were NumPy arrays, all we have to do is just say C equals A plus B. And that's it. So all the magic of doing all that looping is happening inside the NumPy code and not really in the code that we have to write. So what? I mean, this is just syntactic sugar, right? But I don't know. Perl programmers, we like syntactic sugar, right? Everything. All of Perl is syntactic sugar, really. But this is syntactic sugar that has some big advantages. And of course, as we're familiar in Perl, if you write less code, it's already good if you're writing less code, because the less code you write, the less chances you have of making a mistake. But in this case, it's also faster code for a number of reasons. One is that stuff that's happening in the vectorized operation at the bottom, the C equals A plus B, is all happening it's all compiled code. It's all like their equivalent of XS code. So it's running, it's all precompiled. It's not has to be interpreted every time through the loop. It's also super optimized code because it's using under the covers, at least for the linear algebra stuff, BLAS and LATPAC, which are these super optimized Fortran libraries that have been around for forever and like the gold standard in doing this kind of stuff. And you also end up with much more compact data structures because you're forced to have the same data type as for all the elements in there. So the data is a lot smaller. It can do much faster operations on them because the data is more compact. So what they're hoping to accomplish, and what they seem to have pretty much have accomplished, is to have the ease of use of a modern programming language, but to have the performance of super optimized C or Fortran code. And they've managed to do it by keeping all the native Python array syntax with a superset of it as well to do slices and things. So I'll talk a few slides about how to install it. On Debian, it's pretty simple. You can just say apt-get install Python SciPy. SciPy depends on NumPy, so if you just do that, you get pretty much everything that you need. On OS X, the first thing I tried to use, because I use Fink as my normal package manager, was just say Fink install SciPy Pi27. I don't recommend doing that, though, because, I don't know, the first thing it tried to do was install GCC, and because it didn't like the version of GCC I had, and it took hours and hours to install all the prerequisites of all the stuff that it needed. So I think, and I wish I had spent some time when I just got this new Mac, I think most of the NumPy and SciPy stuff seems to come pre-installed with, at least with Mavericks now. And it may have been on the previous versions as well. So don't really, try to test if it might already be installed on your box if you're interested in it. If not, there are binaries available for OS X and for Windows. And obviously the apt-get install is going to be a pre-installed binary. Try to get a pre-installed binary because it's a very, very big package. There's another problem because as you may have heard, there's been issues, just like we've been having issues in the Perl community about moving to Perl 6, and the syntax is quite a bit different. They, I guess, are a little further along with Python 3, but the syntax changes are different. Yeah, people don't really want to change their code from Python 2 to Python 3. It breaks things. If you want to read more about it, read that link that I have there. Yeah, but basically most people have decided to stay on Python 2. So for me, because that's the Python, to the level that I know Python, that's the version I'm using. So those examples usually Python 2.7 and NumPy 1.6. And so I don't know, this is how I feel about that. So how to use NumPy and SciPy. So the first thing you have to do is import the modules. And if you're, this is already a bit of a tricky thing, so I want to spend a few slides talking about this. So you could just do import star from NumPy, import star from SciPy. And this is probably what I do in the examples that are coming up. But of course, that's going to import everything into your local namespace. So if you want to import them and have more control over namespaces, you can do import NumPy as NP, import SciPy as SP. Then you have to put NP dot or SP dot in front of everything. You could also, well, SciPy already includes most of NumPy, so you can get away with just doing import star from SciPy, and that'll get you most of the way. But I don't know, the Python people said I should really do that. So I thought it was one way to do things in Python. I don't know. So do whatever you want. I don't care. So data types. So at a high level, from a Perl point of view, I don't know what they call it in Python, but they basically have, for our purposes, 3 different kinds of data types. They have things that are like scalars in Perl, and they can store anything. They can store numbers or strings or dictionaries and other things that they have in Python. They have lists, which come in square brackets, and they can have different types of data, different data types in them, like that, where we have numbers and the string and a floating point. And they have tuples, which are like lists. The difference between tuples and lists is that lists are mutable and tuples are immutable. And now we can combine them together. Here's our that range and append thing that I had before. And they don't have to be just numbers. So here we're adding 3 and 2 and getting 5. We're adding 1.4 and 7.1 and getting 8.5. But we're also adding pi and a and o. And that ends up concatenating strings together, and we end up with piano. So the way NumPy handles things is they glom onto this array syntax, but they force you to just have a single data type in them instead of multiple data types like you normally can. So if we, in this example, we're just importing, just for simplicity's sake for the slides, I'm just going to import from SciPy and get everything that I need. And then the constructor, so the basic array, the basic data type that is used in NumPy is called array. And you can either pass in literal arrays, like inline arrays like I have here. And here we have integers and floating points. And if we pass that into the constructor, then we end up, x and y will both be the array data type. Of course, they don't have to be literals. You can pre-assign them like I'm doing on this slide as well. And they support a whole bunch of data types. These are mostly the C data types, although they also support complex numbers. There's issues about how it deals with promotions and things like that I'm not going to get into. You can see the documentation for that. Unfortunately, the documentation seems to spend a lot of time dealing with the promotions, dealing with different types of data, different data types, which I don't find very interesting. It kind of gets in the way. So we'll skip by that and just realize that it's some sort of an issue. And we'll get on to the more interesting, at least to me, stuff about how you end up using it. So let's go through a simple example here. Here I'm just making an array that goes from 1 to 9. And there's other ways to do it in Python, but this is a very straightforward way. We're just going to 9 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we want to take a slice of them, we can say a sub 4 colon 6, and these are exclusive ranges. So 4 only goes from 4 to 1 less. It goes from the first one to 1 less than the second one. So that's different than MATLAB. MATLAB has the same syntax, but 4 colon 6 would be 4, 5, and 6. But in Python, it's only the 4th element and the 5th element, but not the 6th one. And also, it starts at 0. It's indexed at 0 instead of 1. So these are all kind of confusing if used in MATLAB. So what this ends up doing is, if I don't step on this, right? 0, 1, 2, 3, 4. This is the 4th one. So it gets the 4th at positions 4 and 5 here, but not 6. So that's why, did I count right? Yeah, so that's why it returns 5 and 6 here. We can also use a slice syntax on the left side of the equal sign as well. So if we assign them to 0, then it zeroes out these elements. So this part is pure Python syntax. This is an extension that array allows that you can't do with normal Python arrays. And then we can also turn it into a 2-dimensional array by using the reshape method. So here A was a 1 row and 9 columns, and here I want to reshape it into something that's 3 by 3, and then what it returns is a 3 by 3 matrix. And it doesn't modify the original array, so if you do the reshape command, you have to assign it to something else. Okay, so now we have a 3 by 3 array. Okay, so that's slicing and reshaping. Okay, so let's show some simple matrix multiplication, matrix operations. Here I'm making 2 arrays. A is going to be 1, 1, 2, 2, and B is 3, 3, 4, 4. We can add them together, and we end up with 4, 4, 6, 6. So it's just doing pairwise addition, just like normal matrix addition. We can subtract them, and we end up with -2, -2, -2, -2. If we multiply them together, this is different than MATLAB, it does pairwise multiplication. So this is the equivalent of MATLAB of dot star. If you want matrix multiplication, you have to use the dot method. And that's because it's really doing dot products between the rows and the columns. And so you have to use dot to do matrix multiplication. And so you end up with 7, 7, 14, 14. OK, we could do other matrix stuff too. So let's walk through this. Here I'm making a two-dimensional matrix, which is 3, 1 in the first row and 1, 3 in the second row. We can take the inverse of the array with the INV function, and that's the inverse of it. We get eigenvalues if you want to do that. The eig function returns the eigenvectors in the v parameter and the eigenvalues in the d parameter. I don't know why they call it d, but that's what it had in the example. Also notice, and this is a little confusing, is that sometimes when you're doing things with NumPy, there are functions like they are here. And other times, like if we back up here, this dot, if you want to do dot, that's a method. I don't know how they decided that some things are methods and some things are functions. I kind of wish they had just kept to one of them. And to be honest, that's kind of why I put them up on the slides instead of trying to type them in here, because I kept getting confused myself about them. I'm certainly coming from a MATLAB point of view, and a lot of NumPy was designed for people to sort of transition from MATLAB into NumPy. Another annoying thing about MATLAB is that we not only is it expensive, but it requires license servers in order to run. The license servers all went down on Drexel like last Thursday, I think, and like basically all afternoon we couldn't do any work because license servers were down. Which again had us started to talk about NumPy after not talking about it for a while.
Well, you can actually, there are incidental licenses, but it's
There are, yes, and we have lots of different licenses. The student license, you can actually run it, standalone, and that's fine. But that doesn't have it doesn't have the compiler which we use. So all of us are running the faculty staff version. So I'm staff, so I can get that version, which has more features, but it's tied to the license server. So if I want to run it, like from here, I have to be in a VPN in order to run it. But that's a good point. And these are some gotchas. One is that array indices start at 0 instead of 1. It uses square brackets, so it uses the array syntax instead of parens like MATLAB does. The ranges are exclusive instead of inclusive. But there's some good things too. You can create functions wherever you want. Like MATLAB, it's a kind of a pain in the butt to create functions. So MATLAB really wants every function to be in a separate file. And this thing about the functions and methods, which I find kind of confusing. There's lots of other things. And in fact, there's an entire page on the NumPy or SciPy website, I forget which one, that just says all the differences between MATLAB and NumPy. But there seem to be equivalent things between them, at least for the basic matrix operations. Also comes with a lot of MATLAB-like tools, although they're really not quite as nice. There's something called IPython, which is an interactive environment, but it's basically like a command line-based interactive environment. There's MATPlotlib, which supports some pretty cool graphing, like function graphing things. And it actually has two different interfaces, PyPlot and PyLab. And the difference is that PyLab's really designed to, if you're using it interactively, because it imports everything into your own namespace, whereas PyPlot splits the namespace out a little bit, so it's better if you're actually writing a program to use it. And you can also say from PyLab import star, and that will get all the PyLab stuff plus SciPy and NumPy and everything. So in some of my examples, I'm actually doing from PyLab import star instead of from SciPy import star. I wanted to walk through one more example of doing vectorized operations. And so this is a close-up of that video I was showing you before. And the stuff on the left, this is kind of a before and after I wrote some code to try to track it a little bit better. And these are, so the problem are these cells, the cells we're tracking, sometimes like to go underneath the layer of the OP9 cells, and they're really hard to track because they only look like dark circles. And so I came up with some way of trying to track them doing that. No, really not at all. No, mostly when they're sitting on top of it, they look like the brightness is really a matter of the phase contrast imaging from that weird like microscope diagram I showed before. But it doesn't. You don't get the diffraction stuff. And they don't show up as well when they go underneath because there's nothing. It's focusing on just the layer, the culture that it's growing in. At any rate.
Are you doing facial recognition on them?
I'm not doing facial recognition. What I'm doing. Okay, so the problem is you can't just look for dark circles because there's dark circles all over the place in there. You really want to look for dark circles in a very confined area. So if we know where it was on one frame, we know that it hasn't moved very far. So we will look for dark circles in a much smaller area, and it works better. So I'm not going to show you how I did this, but in order to draw all these things on the screen, I had to do something kind of comparable. So I'm going to show you how to just draw a circle. And you might remember from math class, this is the equation for a circle. It's so if we think of the center of the circle as being AB, we want to find all the points such that x minus a squared plus y minus b squared equals r squared. And you can take the square root of both sides, but if you don't take it, then you can work with integer math instead of floating point math. So we're going to try to find all the points inside here. We're going to make those all white. So that's a 100 by 100 grid. But I'm going to work with just a 10 by 10 grid for the example. So we'll step by step how this all works. And a lot of these are really common idioms, at least in MATLAB, that we use every day. So the first thing I'm going to do is I'm going to make a black and white. So that's why I'm calling it BW. I want to make a 10 by 10 matrix of zeros. And there's a function just called zeros. And you pass in 10, 10, and I get a 10 by 10 array of zeros. And what I want to do is put a bunch of ones to sort of simulate a circle in there. Okay, I'm calling it B and W because it's either going to be black, which is 0, or 1, which is white. All right? So if I say BW greater than or equal to 0, they're all greater than or equal to 0 because everything was 0. So if I do that, then it returns a 10 by 10 matrix of truths, which is what this is. And in this case, it tells me that the data type is Boolean. But OK, so BW is all zeros. BW greater than or equal to 0 is all 10 by 10 truths. All right. OK, so now there's a method. So in MATLAB, it's easier because MATLAB, this function is called find. But I don't know why they didn't call it find. Maybe find is being used for something else in Python. So they call it non-zero. So if I say non-zero, then remember BW greater than or equal to 0 is all true. So true is greater than or equal to 0. So all of them are non-zero. And what this returns is two vectors. And let me walk around here. You have to look at them in pairs. So this is the row and column of the first one. This is the row and column of the second one. This is the row and column of the third one. So it returns the row and column positions of everything that matches. In this case, everything matched. So what I have is this is 100 elements in it, this is 100 elements in it. And if I look at them in pairs, if I look at the ith element, I'm going to get the ith row and column that it was true on. And this is, and we can assign them to things. And here I'm going to assign them to R and C. So R is row and C is column. This is a really, really common idiom in MATLAB. But in MATLAB, you just say find, and it's a bit clearer what it's doing. So often you want to find these row and columns, and you can kind of iterate over the rows and columns. In fact, you don't even want to iterate on them. You want to use vectorized operations because they're a lot faster. So, all right, so now we just have the coordinates of everything. What do we do with the coordinates? OK, so let's define what the center of the array to be. We're going to put that at 4, 4. I want the radius to be 2. This is the magic command here. So let me walk through what this does. So I want remember, this C is really a vector of things. So when I take C minus the center of 0, so that's going to be C minus 4. Right? C are all those numbers. So when I do this, I'm going to get another vector of things where I've subtracted 4 from everything. And then that whole vector I'm going to square. That star star 2 is square. So now I have squares of the columns, right? So the x distance, the squared x distance away from things. And I'm going to do the same thing here. I have this all the r's, and I'm going to subtract 4 from those, this position here, from all of them. I have another 100 things. I'm going to square all of those, and then I'm going to add these things together. So now I have 100 things where all I'm going to add the square distance in the x position and the y position. That's a formula I showed from before. And because the rows and columns all are paired up, I can go from this to the positions in the original matrix. And they all get stored in dist. Now dist is it's a vector, so I have to reshape it to 10 by 10, and I end up with this. And now I have this 10 by 10 matrix where everything is the square of the distance away from this point right here. So Jay's getting it.
Tricksy, man.
And, OK, so that's dist. So what do you do with dist? So I can look for everything where the dist is greater than or is less than or equal to the square of the radius. And I want to set those things in BW to be 1. And these things are all set to 1 now. And let me, if I go one more. And it looks like a diamond because it's only 10 by 10. But if it's 100 by 100, it will look more like what I showed you before. And everyone following this? This is what I do all day long, pretty much. And here's the entire program, and it's not very long. And we have to actually display it. And to display it, there's a command called imshow, which is exactly from MATLAB. And you have to say I want it to be grayscale. That's what set CMAP does. And then you have to show it, and you end up looking with something that looks like this. And it looks more like a circle than that diamond thing I showed you before. But so one thing to point out is that there's no loops in this. Like here's the code, and there's no loops. And because the loops are all happening inside the compiled NumPy code, which is really cool. And it takes a while to start thinking in terms of this way. I mean, I still kind of think in terms of I want to do loops for everything. But you pretty much never you want to avoid loops as much as possible when you have access to these vectorized operations. OK, so that's like a really brief introduction to NumPy. Let's talk about SciPy a little bit. So if you look at the SciPy website, there's something called like subpackages. They list a few things. So there's linear algebra. I showed some examples of that. They have statistics, Fourier transforms, interpolation, all the things you would kind of expect to be there. But there's actually a lot more than this. I'll show you in a few slides. I mentioned Matplotlib before. If you go to that URL, you can see a gallery of things. Here's one kind of cool looking graph just from the examples.
Inverted MATLAB.
What?
It looks like the inverted, MATLAB has that, so it looks like it's like inverted MATLAB.
Yeah, a little bit like that. And I mean, I'm not going to walk through it, but this is the code that generated this cool picture here. I don't know. This is why I decided to not do syntax highlighting, because I didn't think it would be readable. But this is like all the code, right? And because it knows how to do surface contours and stuff like that. So, like, what about PDL? Like, every time I've talked about the NumPy and how cool I think it is, people ask, "So, what about Perl data language? Like, why aren't you using that?"
Because it doesn't have MATLAB live.
What?
Because it doesn't have MATLAB live.
Yeah, well, I mean, it's not as well integrated into the language. And from talking to Rick, he said it's hard to do it because we have tied variables and things. It's hard to just rip out the guts of array and replace them with these nice vectorized operations. So they have to use objects. So it's not, the syntax isn't quite as nice. I mean, the nice thing about NumPy is even if all you want to be able to do is just kind of pack the data in, you almost get that for free. You just use the array construct. And you can just keep using them like regular arrays, except they're using less space and will be more efficient. I don't know if it has support for BLAST and LATPACK. I saw a module from 2004. It didn't look like it had been updated since then, so I don't know. There's a really tiny community. Mostly people doing astronomy are using this, although I do know a lot of astronomers who are using, I know some astronomers at Drexel are using NumPy too, so. And it's like not really as well integrated. I mean, it would be nice if I was doing something with graphics, I get a matrix back, I could use that matrix to do linear algebra on it, things like that you would want to use. And these things just are not really well integrated, certainly not to the extent that they are in Python. So like Python's really kicking our ass in terms of scientific programming. I kind of feel like almost we've lost an entire generation of programmers who are, I mean, Perl's great for doing string processing, and if you're doing with like BioPerl stuff, but for doing number crunching, it's just, I wouldn't recommend anyone to try to use Perl if you're in grad school to do number crunching stuff, because NumPy is just Python's a lot better for it. I mean, they have a big community of people. They have, coming up in a few weeks, or maybe next week, is SciPy 2014. I think, I don't know how many people are going. I think that it's a bigger conference just for NumPy and SciPy than YAPC is. So it's a 6-day conference with poster sessions and invited speakers and things. I looked into all kinds of cool stuff. And it's just the community just doing numerical stuff, just doing number crunching in Python. Here's some other projects that use it, OpenCV and Scikit and Inkscape. Lots of projects that maybe you don't even realize are using it. Here's some to learn more. One thing I want to get to is the topical. I like to show people this when I do this talk. If I can find, where's the topical? I have no idea what my resolution is now. Okay, so I know you can't read it, but I'm just going to kind of skim through what's here. Working environments, some basic tools, wrapping code in like boost.python where we have plotting stuff, data visualization, LaTeX support, 3D programming, optimization, nonlinear equations, I don't know, parallel programming in here, astronomy, artificial intelligence, statistics, bio stuff. I mean, it just kind of goes on and on and on. Molecular modeling. All these people are using NumPy and SciPy to do their stuff. And I mean, are there any? I mean, a lot of these things. I don't believe that there's any Perl equivalent to doing any of these stuff, because all these people have moved on and are using Python instead. So. Go back here, and I will leave you, because that's kind of a downer, that I wanted to leave you this cool image that we did in our lab. And this is actually not done using MATLAB. This is done using, so there's 3D. So they also have microscopes that can do 3D imaging. And these are, I don't know, this is the subventricular zone, so some part of a rat's brain, some tiny little part of a mat's brain. I think it's maybe like less than a millimeter big. They have special microscopes to do 3D imaging on them. And so the big image that's all around is probably about 50 or 60 images that have been montaged together to make one image. And this is just showing that you can zoom in and zoom out and look at the structure at different kinds of levels, which is very cool. So I'll leave that going, because I think it's just a really cool image. And I think I finished maybe a little bit early. So does anyone have any questions? Yeah.
So I thought image processing, when you're chasing things around, was all about edge detection. So I'm trying to understand the vectorized circle thing, where you're drawing circles and vectors. How does that? I mean, like when you're actually trying to chase these.
Oh, well, one thing that I've been doing is, so we often have, for the movies I'm working on now, we have more than one channel. So there's the image with the phase contrast image. It looks kind of like what we saw, but then there might be parallel frames that show the different fluorescence images. So they'll have they took one picture with visual light. They took another picture where they showed a particular wavelength of ultraviolet light and got some reflection back. And so that would be just the green image. Another one would be the blue ones. And then I want to take those and superimpose them on the original image. So I want to find those pixels, the ones that have been lit up, and then draw them on top of the other ones. So I'm kind of doing similar stuff. I'm not doing exactly that. That was just kind of a simpler example. But those sorts of things with doing vectorized stuff and trying to take some of the points and doing a find and putting them on top of something else. I mean, that technique is something that I use all the time. Yes?
Because Perl 6 has representational polymorphism, it will be pretty easy to actually stitch NumPy in as a representation technique.
Awesome.
If somebody is interested in doing something like that, championing it, feel free. Volunteer.
Okay. That's good to know. Yes?
Well, it depends a little bit. It's a little bit used more outside the astronomy community. I mean, I know Shutterstock uses it. Maggie, she wrote some stuff, some statistical stuff in Quiddle, but and like I say, maybe talk to Dave Mertens about Quiddle stuff. But anyways, whereas Python related though, and Windows, I was looking at I gave a talk in Pittsburgh for a workshop talking about MATLAB and some options to what Perl can do in Python. And in Windows, there's this distro called Python XY. And it's like a kitchen sink. I mean, for the people that have to, at the time I was supporting a lot of Windows machines. And it's like, oh, this is the distro to use. It's called Python XY. And it brings the kitchen sink of NumPy, SciPy, and it's like, it's really close to being a MATLAB killer in terms of.
And it does it in what? In Python or in
Python?
Perl? Yeah.
It's Python. Yeah, so,
yeah,
but it looks like they use, I can't remember the name of the IDE, they have like it plays like MATLAB, but it's all Python. No, there's another one called Python XY.
Yeah, I think that's come up in our lab. It's the thing that makes it hard for us to move away from MATLAB is not that we really like the language, but we like the environment that you run the language in with the debugger is very nice.
Yeah, I mean, MATLAB is really integrated in how it does because they have a lot of money to throw at a lot of the problems. But in terms of if there was one alternative to MATLAB, I think Python XY is a really solid alternative. I mean, even more so than like Scilab and Octave, the MATLAB clones. Just because there's the Python depth behind it.
Yeah, right. And I also think maybe this is, I don't know if this is like a flaw in our community or not, that I think that there's a lot of people that do work on like kind of reinventing the wheel and trying to make one thing and trying to make it better or more suited to their own environment, their own workplace, but not a lot in terms of having one thing that everyone can use and can, people that had various modules can all play with each other really well. And I think Python does a much better job of that. But everyone says, okay, NumPy is what we're going to use, so NumPy is cool. And then we'll all kind of support that.
One true way philosophy, right?
Yeah.
It's like, this is it, done. There's no tiptoeing. So it's easier to do that. And so, I don't know, we've got n different ways of doing web front ends and in different ways of doing templating, and they've got 500 packages all using the one module to do all sorts of things. So I don't know who's ahead or who's not, but it's a big difference between our communities.
Why do the stem cells move around so much? What are they trying to do?
Well, it depends on the type of stem cell. There are other people in the lab who are working with neural stem cells, and those tend to not move around very much. These are because these are part of the immune system, which are like our white blood cells. They're designed really to move around and try to attack whatever the disease is in your body. So they're just by their nature pretty motile cells.
I didn't know there were stem cells that did that.
They're not, and I think I'm not even sure that you would. I mean, I'm not a biologist. I'm a computer scientist, but maybe precursor cells. I mean, the cells that we're interested in studying are cells that, when they divide, become potentially other sorts of things. Whereas most cells, when they divide, become two of the original type of cell. So, whether you want to call them, I don't know, precursor cells, which some biologists do. We call them stem cells because what do we know? We're like electrical engineers and computer scientists, right? But right, they move around so much because they're blood cells, and that's kind of what they do. Oh, interesting. Sometimes when they divide, they tend to clump together for a while too. So so they kind of do both. They kind of do both. Sometimes they move around quite a bit, and other times they'll just kind of lump together. Maybe towards the end of the movies, where they're kind of dying, they don't move around as much. I don't know. Any other questions? Okay.
Do you tend to throw a lot of different alternatives at the researchers, and then they kind of pick the ones that look the coolest for their? I mean, like, how do you when you have all these parallel layers and you're trying to overlay things on top of other things?
What do you mean by things in researchers?
Never mind. This is probably a long conversation.
Are you talking about tools, or are you talking about
when he was saying?
Okay, well, maybe I can try to answer the question, or at least when we have new movies from biologists, we certainly throw the kitchen sink at them and try to determine what's going to work. And when you read the paper, you just read about the one that worked, and you don't read about the 10 ones that didn't work. So we definitely do that. And of course, if we want to have these movies, we try to pick the ones that we look nice and have lots of cells moving around in them as well. Was that answering your question?
Yeah.
And oh yeah, and we try to make the movies look really nice so that they look good in presentations, and we'll try to clean them up and make them look, as nice as we can for either publications or for presentations. And this is, I don't know how many versions of this movie that have been done, just because it looks so cool. This is done they use because my boss used to work for Microsoft. This is done on big honking Windows machines with crazy graphics cards, and so the montaging and everything was done with CUDA, and the actual imaging, our imaging, like the back end imaging, front end imaging, whatever. What we're seeing is actually done in DirectX. One of the grad students did who's a game programmer for a while, and just had to do a lot of that stuff, and with big data sets, yeah.
Yeah, it's interesting. Speaking of the visualization, it's like Professor friend, she was borrowing ideas for some visualization stuff from the gaming world, because they know how they have to know how to talk to these GPUs and stuff, and let alone and in terms of talking to the hardware layer, but also the techniques they use to render and stuff like that, and then apply. Yeah, that's
exactly what we're doing, and plus they're relatively inexpensive. Because the gaming community is driving there's so much demand from the gaming community that drives the prices down. We're also working. We're working at ways like once you have a 3D version of the cell like this, and actually I don't know if this one is like that, but this is just a still image, but there's about 100 frames of this movie too that you can kind of go back and forth and watch the cells dividing, we've been experimenting with different ways of how to use the program like this, and we've done an experiment with a leaf, one of those those sensors where you kind of move your hands over and move in like that. We have someone in the lab who's working on a haptic control with a glove, and you kind of move your hand in and move your hand out.
Are you doing any cave stuff in terms of like a 3D viz kind of? No,
we're not doing that. So we have. What we do, kind of similar, that we have a 3D projector in our lab, so you can put
you can put
goggles on and see it in 3D.
Right,
yeah, it's very cool.
In terms of
Yes, we do that. And this looks even cooler in 3D than it does in 2D.
Yeah, it's amazing. I mean, there's like say
the colors all mean different things too, and I don't have that up here on the slide what the different colors are. I think the red is blood vessels, and the other ones I don't know what they are.
Axon or something. It's
yeah.
Brain, yeah. But yeah, I mean, it's amazing. Like they're talking about GPU prices going down. The ability to do 3D visualization, the costs are just dropping too because of projector prices.
They're not going down. They're apparently not going down for 3D microscopes. So the 3D microscopes are still very, very expensive.
But 3D viz for the guys that collect the data and can look at it 3D later.
So we're having, we only have a few people who can provide us with 3D images off of the microscopes, and
That's just especially because there's no one else wanting a 3D microscope, but everybody, like Oculus Rift, right? We have a commercial.
Well, actually the problem is, I mean, I think a lot of people would like to do it, but they're not quite sure. I mean, the tools aren't there to really use it, and so what you get out of it are, I mean, all the software I think universally is crap that's provided with the microscopes. Mm-hmm. So I don't think they have anything even to join all the images together. I actually don't work with that, so I don't know for sure. But one of the issues that we have in 2D is it's really hard to tell when the cells, after they've undergone mitosis, it's hard to, when they're right next to each other, it's very hard to tell one cell from the other cell because there's not a good border between them. And it's much easier in 3 dimensions. You can kind of zoom all around. You have a lot more areas to look for the cells. So they're not on top of each other in 3 dimensions. It's only in 2 dimensions that they look like they're on top of each other.
I just remember I had a friend who was his master's thesis on tribology in terms of like, when you're doing machining and taking pictures as the material's getting sheared off, and then he used MATLAB to take pictures of it and to treat the metal as a fluid flow because he's an aerospace engineer. But he's able to do like point tracking, right? See how the metal was going.
Yeah, it's always cool when you can get people from different fields because they look at a problem, with different, from a different point of view. And I think we hope that that's what we're providing to the bioimaging community as well. Right. That we can, we're good at kind of doing the segmentation stuff, and so we're hoping that we can help out the biologists in doing stuff. And there's another step beyond those like stem cell movies that I show you that will really. Being able to track them and build the lineage trees is already kind of cool, but I mean, at some point you want to know, the big question is how they decide to differentiate, how do they decide to become one cell versus another cell.
Looking around the environment around them, right?
Well, and their behavior changes sometimes right before, so that's the higher level stuff that we're working on.
Use per step, so if you can track the lineage.
Right, but I mean, just tracking the cells and building a lineage tree automatically is already that's a big problem already. And it's very hard to do. People that have done it by hand, and it's hard to do by hand, and they make lots of mistakes. And so anyway, so let me get out of here. So I'm probably like over time now, so like eating into lunchtime. So thanks a lot.